Good evening, everyone. For this demo presentation, I'll be covering our work, attestation capable programmable switch. To give a brief motivation for the reason for our work, in a networking data plane, traditionally, uh, switch components used to have fixed function ASICs. And by that, I mean the vendors would provide predefined protocols and predefined functionalities, and the end user would have to select from within those functionalities. The trend has been to move from fixed function to programmable ASICs. With programmability, the end user can now program their own custom protocols, their own functionalities, and they can deploy it quickly. However, the programmable nature of the ASIC increases the attack vector because now you can have a malicious entity load their own program onto the programmable ASIC, or even take control of the control plane and modify it such that the data plane starts behaving differently. In such networking data planes with programmable elements, how do we identify a compromised network? We use a framework, as mentioned in the paper, a case for remote attestation in programmable data planes. In essence, it talks of a framework in which there are a couple of primary units. One of the units is called an attester. It is a programmable element that generates evidence. And this evidence is then shared with a second unit called a verifier. And as the name suggests, the verifier ensures that the evidence generated is correct. If it isn't, then it communicates to the end hosts, informing them that the network data plane is compromised. In this demo, we'll be running this attestation capable switch on the Fabric research testbed. So you will see a couple of commands to set up resources in Fabric. The topology of the experiment is as shown over here. It essentially these are all VMs. So there's a VM that runs the BMV2 software switch, which acts as a programmable element. There is a VM that sends packets, and there's a VM that receives the packet. Once I get the resources from Fabric, I'll be starting the switch, send the packets, and what we'll see is based on the rules that has been programmed for the tables, evidence is generated by the switch, and that evidence will be visible. Similarly, when we modify the rules, the evidence will change accordingly. If time permits, I will try to show the performance throughput of the switch as well. To start off, these are some commands to set up the resources. Fabric uses a library called fablib, through which it's a set of APIs through which we can request resources. So the first step is I'm just defining a couple of constants. In our case, the programmable element is going to act as a router. So we have the sending host in one subnet and the receiving host in another subnet. And these are IPv6 addresses. And as a result, I'm mentioning this to Fabric saying that I want host 1 to be in one IP subnet and host 2 to be in another IPv6 subnet. Similarly, I ask for a couple of resources, so 2 cores, 8 GB of RAM, etc. Once I have all these things, I then ask for some network interface card so that we can have the network connection, set up the L2 network, which means setting up the connections between all the different VMs. And once I have all the resources configured, I request Fabric for the slice or for the resources. Once I have the resources, I log in and I download some common libraries and tools. I have a set of custom scripts that are required to set up the environment. So I'm copying it from this system over to the VMs. That's what these commands do. Then I execute the copied script so that the environment is set up correctly. At this point, we have all the systems up and running and the environment is set up. So I'll be showing the experiment now. Just a second as I log into this host. Okay. The first thing is I'm going to start the switch. I'm going to use a script. Essentially, what it's doing is it's checking that the program that has to be loaded onto the switch is built. If it isn't, then it's going to build the program, and then it's going to start the switch and pass the program as an argument. So now I started the switch. 2 ports have come up. Second is I'm going to start the server on the receiver node. We're using iperf to send packets and receive packets. Over here, I have another script called run iperf sender. And what this is doing is it's saying send packets to this IP address, which is the IP address of the receiver. Send UDP packets at 100 Mbps, and the length of the payload is 1300 bytes. Now, if I send packets, nothing is going to be received over here because there are no rules at present on this program. So I stop this and then I add some rules. For the rules, essentially what's happening over here is there are a couple of tables, but what the primary concern is you have an IPv6 address. It says if you see this IPv6 address, then send it out through port 1. Similarly, if this is the IPv6 address that you see, set the destination MAC to the receiver MAC address and set the source MAC address to my egress MAC, the interface egress interface's MAC address on the switch. I now add the rules. So now the rules have been added, and I'm also printing out the hash values, so the evidence is generated from these rules. So the registers, they're not being used in this program, so they just have some default value. The tables, I have this value. This is based on the rules that we have, and the program hash as well. Now when I send packets, so over here I'm going to start a TCP dump so that we can see the packets. Now I'm going to send the packets. While it's sending, I just highlighted the relevant portions. Based on this over here, you can see there is a 3764, which is the HBH ID, and the length in hexadecimal 64 is 100. These 4 bytes are not used. And then from here onwards, we have the switch register value, the table register values, the evidence has been generated, and the switch program value. Similarly, there's a set of path register values, path table values. Now, if I modify the rules, in this step, basically, I'm just adding one more entry. And as a result, the table hash has changed. If I were to send another packet, send another set of packets, again, as you can see, based on the previous values, you have the hop by hop extensions, and then the switch register value. But at this point, you can see the switch table values have changed, and they are consistent with the values that we see over here, E7, A0, etc. If I were to delete the rule, now I get back to the previous value, which is 1696. When I resend the packet, let me start this. When I resend the packet, once again, I can see 3764, and based on this, we have the register hash value and then the table hash value, which is what we see over here, the previous value of 1696, etc. As a result, we can see that our switch is able to create the evidence and act as an attester. If there are any further questions, please let me know at this email address. Thank you so much.